Today, we're going to talk about shader optimization. Let's go. So we're in the middle of a series of videos about performance optimization. In previous videos, I've gone over a big set of all kinds of things you can do to make your project run faster. And then last week, we used picks to identify a set of expensive draw calls in our scene and started a process of optimizing them. If you haven't seen the rest of the videos in this series yet, I'll link the playlist down in the description so you can catch up. So what I'm going to do today is show you a set of optimization techniques that you can apply to your shaders. And then we're going to use those techniques to optimize the slowest draw calls in both Unreal and Unity. I've grouped our shader optimization techniques into 3 categories so they're easier to understand and remember. So here they are: optimize texture sampling, do less math, and do math in the right place. And under each of these categories, there are some more specific tips and principles to follow. So let's jump in and talk about each of these. First of all, optimize texture sampling. Texture sampling is the most expensive operation a GPU does. A graphics processor can typically do math really fast, but when you tell it to sample a texture, it first has to do extra calculations to figure out what MIP level of the texture to sample, and then it has to send the request for the texture data that's stored in VRAM or graphics memory, and then wait for the result to come back. Sometimes the compiler can reorganize the order of things so that the GPU does other work in parallel while it's waiting for the data to come back. But if there isn't enough other work to do, the GPU may end up sitting idle, waiting for the texture data to come back from memory. Because it's the most expensive operation, you can get great performance improvements by optimizing the texture sampling in the following ways. First, sample fewer textures. Reducing the number of texture samples that your shader is doing is the most effective method for improving shader performance. In my experience, the performance cost of a shader scales linearly with the number of texture samples it does. A texture sample has the same performance cost regardless of the number of channels in the texture. A texture can have between 1 and 4 channels. A single channel texture costs the same to sample as a 4-channel texture. So you can reduce the number of texture samples you're doing in the shader by packing data together carefully. For example, you might take an object that's using a color, normal, and mask texture and repack the textures so that you have color and smoothness in one texture and normal, metallic, and occlusion in the second texture. Now your shader is just doing 2 texture samples instead of 3. And I have a couple of other videos on this specific topic that I'll link down in the description. If your color texture is mostly all one color, you could convert it into a grayscale image and then pack that single channel data into a free channel of another texture, and then in the shader, convert it back into color by multiplying it by a color parameter. Sometimes packing data to reduce the total number of texture samples results in using more texture memory. For example, textures that use 4 channels are usually double the size in memory compared with textures that use 3 channels. Increasing the memory use in this way to reduce texture samples is almost always an acceptable trade-off because the game engine can stream textures in and out to make them fit into memory when needed, but there's no way to give it more GPU compute time. So trading texture memory for GPU performance is a good trade. All right, next we're going to talk about lowering texture resolution. When a texture is lower resolution, the GPU can sample it faster. This is especially true when the GPU can fit the entire texture into its cache. Alright, so what is that? Well, the GPU has a small cache of memory that is very fast. And when you tell the GPU to sample a texture, it goes and grabs the data that you asked for from VRAM. But it also grabs all of the data that's around that data that you asked for as well. And it stores that extra data in the cache. And it does this just in case the next texture sample is right next to the current one that you just did. So if the GPU can find texture data it needs in its cache instead of in VRAM, it's a lot faster to sample. So if you can make your texture small enough that the whole thing fits into the GPU's cache, the sampling will be incredibly fast compared to a normal texture. The GPU cache is pretty small, so you may need to make your texture 32 by 32 or 64 by 64, obviously depending on the GPU that we're talking about, in order for it to fit all in that cache. Most textures need to be larger than that, but if you can make your texture small enough, it's a big win. Even if your texture needs to be larger, you should be careful to make it only as large as it needs to be. A 1024 texture will sample faster than a 4096 texture, for example. So take the time to look at each of your textures and size them according to the detail they contain. If the detail is low frequency, you may be able to make them smaller than you thought. Keep in mind that textures in a material don't all need to be the same size. You may be able to make your color texture or your mask texture a lower resolution than your normal map. It really depends on the frequency of change in each of the textures. Alright, compressed textures. This one is fairly obvious. Use the appropriate type of texture compression for each of your textures. The GPU can sample compressed textures faster than it can sample uncompressed textures. This is because it has to transfer less data between the VRAM, the texture memory, and the GPU. In some rare cases, it's okay to use uncompressed textures. When a texture is shared by multiple objects in the scene, or when a texture is really low resolution, like 256 by 256, for example, it's okay to set that texture to be uncompressed. But you should only do that if the texture compression introduces artifacts that reduce visual quality. All right, I know we've been talking about making your textures smaller and using texture compression. And normally we think about these things in terms of saving VRAM. But in this case, we're talking about them in terms of making the GPU calculations faster, because you can actually sample those textures faster if they use correct compression and their lower resolution. I just wanted to make that clear. All right, the last one here is reduced texture filtering. Now, when you sample a texture, the GPU does some additional work to filter the result to reduce the noise that would otherwise occur. Because of camera distance and surface angle, the pixels in the texture don't match one-to-one with the pixels on the screen, so filtering needs to be applied to reduce shimmering. And this shimmering is one of the defining visual characteristics of games on the PlayStation 1 because it lacked any hardware texture filtering. Now, the GPU has a range of filtering options that it can perform for improved image quality, including bilinear versus trilinear filtering and the various levels of anisotropic filtering that can be applied. On some textures, the type and quality of filtering can be reduced for improved performance. But be sure to check the results visually so that image quality isn't reduced too much. All right, let's move on to our second category, which is do less math. Aside from texture samples, math computations also require time on the GPU. Doing fewer operations means the GPU can complete its work faster, so anything you can do to reduce the amount of math the GPU is doing will result in faster shaders. Here's some examples. First, use simplified math. When dealing with complex equations, refactor them to reduce the number of operations required to calculate them. Next, don't calculate things multiple times. If you calculate a result in one part of your shader, make sure that you share that result in other places that need that same result. Don't calculate the result for something multiple times. It's a waste of resources. This can be especially tricky when using subgraphs. Sometimes the compiler will notice if you do the same calculation twice and take care of this optimization for you, but sometimes it won't. So make sure that you're not doing things multiple times. All right, next, don't over-normalize. Normalizing a vector requires a square root calculation, which is fairly expensive to perform. There are many places where it is technically correct to add a normalize, but you may be able to get away with not calculating a normalize in order to gain back some performance. So when you add a normalized node, check to see if you can see the difference with and without it. If you can't, leave out the normalize to make the shader cheaper. Some nodes already do the normalization operation internally, and it helps to know when that's happening so you don't have to repeat it. All right, and then finally, let's talk about pixel clip in this category. In shaders that use transparency or alpha clipping, as soon as you know in the shader that the result of the shader is going to be nothing, you can use a clip instruction to tell the GPU to stop running the shader and discard the current pixel. This will allow the GPU to skip the rest of the shader and save some calculation time. For example, if you sample the alpha channel of your texture and the sample is black, right then you know that the final pixel is going to be alpha clipped or 100% transparent no matter what the rest of the shader is doing, so there's really no point in calculating the rest of the results. You can use the HLSL clip intrinsic function at that point to tell the GPU not to continue. And we'll get into more details of this a little bit later on. Now, this clipping operation only works if all 4 pixels of the current quad group are clipped, because the GPU operates on pixels in sets of 4, so it only clips out that pixel if all 4 of the pixels in that group need to be clipped. All right, let's talk about our final category here, doing math in the right place. When performing calculations for a game, there are a lot of different places and times where those calculations can be done. The least expensive calculations are performed once outside the context of the running game and then passed in. And let me explain what I mean by that. If you need to tint the color of a texture, it's a lot cheaper to do that tinting operation offline in your photo editing software than to do that calculation every pixel on every frame of your game. I hope that makes sense. So let's take a look at this list. Here's a list of places where calculations can be performed in order from least expensive to most expensive. So here at the top, we have that example we just talked about, doing a calculation once offline outside the context of the game, and then doing the calculation once on the CPU when the level is loaded, and then number 3, occasionally, like once a second, for example, doing that calculation on the CPU, and then doing that calculation on the CPU once every frame, and then doing that calculation on the GPU once for every vertex for every frame, and then finally, the most expensive thing you can do, calculating this thing on the GPU once for every pixel for every frame. So in that color example that we talked about, if you multiply your texture by a color, you're doing number 6 here. You're calculating every pixel, every frame. You're doing that multiply operation to calculate combining that color with your texture. Whereas if you know that you're only going to do that operation once, you're only using that texture once, it's only ever going to be multiplied by a green color, for example, you could do that multiplication offline in your photo editing software and then remove it from your pixel shader, and that would be significantly more efficient because you're only doing that calculation once and you're not even doing it in your game instead of doing it every pixel, every frame. Okay, the same is true for a lot of other operations. Anything you can do to move operations from the bottom of this list further up the list will result in performance improvements. So, for example, you'll want to move work from the pixel shader to the vertex shader. If there are operations that are happening in the pixel shader that have a low frequency of change, you can instead calculate those operations in the vertex shader and then pass the result to the pixel shader. Operations are generally cheaper to calculate in the vertex shader because typically, and there are fewer vertices than pixels. For example, scrolling UV coordinates can be calculated in the vertex shader and then passed to the pixel shader for use. Now, there is a cost for the interpolation process of passing data from the vertex shader to the pixel shader. So if you do move operations to the vertex shader, be sure to measure the results to make sure that it made a difference to your performance. All right, and then similarly, you also may want to move work to the CPU. If you're doing calculations in the pixel shader and the answer is always the same for every pixel, you can do that math in a script on the CPU or in a blueprint and then pass the result to the pixel shader. That way, you're only doing the math one time per frame instead of over and over for every pixel of the frame. For example, if you need to control the rate of the time parameter, it's technically cheaper to do that rate control on the CPU and then pass in your modified time parameter to your shader. All right, so we've gone over all of my shader performance principles here, divided into these 3 categories. We talked about optimizing shader sampling, we talked about doing less math, and we talked about doing math in the right place. All right, let's take a look in Unity, and we'll take a look at a bunch of the shaders that we identified last week and see where we can apply these principles. All right, here we are in our Unity project, and what we're going to do is take the principles that we just talked about for shader optimization and apply them to the most expensive shaders that we have here in our Unity project. So last time we used pix to analyze our draw calls, and what we discovered is that we have these draw calls, and I kind of ordered them in the order of how expensive they are. So ferns were the ones that were taking longest to draw, followed by terrain, then moss, nettle, rock, and grass. So we're going to optimize our shaders in that order, kind of from highest priority down to lower priority. So let's take a look at our ferns first. Here's our fern shader. We just kind of zoom out here. You can see here up at the top, this is the logic that's running in the Vertex program to make the ferns wave in the wind. And then down here at the bottom, we have the pixel shader that's actually creating the color and the material properties of the fern. The thing that I notice about this, and it's really helpful when you're in Unity's shader graph, if you set the color mode from none to category, because then each of the nodes are shaded by what category they're in. And these red nodes are the ones that are doing the texture samples. So Here's a texture that is for the color. Here's a texture that is for the mask maps. Here is a texture that's doing our thickness map. And then here's a texture over here that's doing our normal map. So our ferns are actually doing 4 texture samples. And what we should do is take a look at those textures and see if they're actually doing anything for us. See if it's worth doing 4 texture samples. Because like we said a minute ago, texture samples are the most expensive thing that a shader does. And doing 4 of them may be a little expensive for these ferns. So here is our color texture. You can see we've got our color in the red, green, and blue channels. And we've got our alpha cutout map there in the alpha channel. Okay, so here is our fern mask map texture. This stores metalness, occlusion, and smoothness. Here you can see in our metalness, obviously ferns aren't metal, so we've got a black channel there. This is our occlusion channel, our green channel, and it's just solid white, basically. So we're not really using occlusion. We're not using our blue channel either. It's just flat blue. And then we have our smoothness stored here in the alpha channel. So from this mask map, we're only really using just the alpha channel, and that's it. Then obviously we have our normal map, and that looks good. And then we have our thickness mask here, and you can see its texture type is set to single channel. So of these 4 textures, we're making pretty good use of our normal map and our color map, but our mask map is only using smoothness, and our thickness map is only 1 channel already. So what I'm going to do to optimize this shader is I'm going to pack all of the information from the normal map, the mask map, and the thickness map into 1 texture. And this is what that texture looks like. I've got the X and the Y of the normal map in the red and green channels. And then I've got the thickness map in the blue channel. And I've got the smoothness in the alpha channel. So I've basically taken 3 textures and packed them into 1. And then I reorganize the shader so that I can unpack that data. So here you can see I've got my base map texture with my alpha channel. And then for my normal map, here I'm unpacking my normal. And I'm also using my thickness map from the blue channel, kind of passing it down to this section of the shader. And then I'm using my smoothness from the alpha channel. And I'm able to take this shader that was doing 4 texture samples down to just doing 2 texture samples. Able to do some great performance improvement there. So I'm going to go ahead and assign this optimized shader to all of my fern materials, and then we'll move on to our next one. All right, so here is my fern material, and instead of the fern shader, I'm going to come here to shader graphs, and I'm going to pick fern optimized, and you can take a look here and see if there was any quality loss. Let's just kind of switch back and forth here. Here's fern optimized. And here's fern. Not a whole lot of difference. There may be just a little bit of subtle difference, but you know, you really have to switch back and forth to be able to tell. If this is set to fern, and now we're looking at fern optimized, there's a little bit of a difference, but I don't think it's too big of a quality loss. Okay, let's take a look at our list again. Looks like next we have terrain. Now I do have something kind of interesting to tell you guys, and that is once we're done with this series on performance optimization, the next series that I'm going to do is specifically about terrain shaders. So I'm going to be going into a lot of detail. We're going to have a whole bunch of episodes on creating shaders for terrain. And what that means for today is I'm not going to spend a whole lot of time going into all of the details specifically of what I'm doing to optimize our terrain shader here in this project, because we're going to have a whole series of videos that are dedicated specifically to that. But what I will say is, well, let's go ahead and pick our terrain here. And if I switch over to our terrain settings tab, you can see we're just using our standard terrain lit shader, which is written in code. And what I've done to optimize this one is I've created a shader in Shader Graph that's not written in code. And this code version of the shader uses 3 textures per layer. And what I've done is, in my version that's written in Shader Graph, I've repacked the texture data in the layers so that I'm just using two texture samples per layer instead of 3. And what that does overall for the shader is, this shader that's written in code is doing 13 texture samples, which is quite a lot. But by switching to the version that I've created, it's called Terrain Simple. You can see that the tiling is a little bit different as we switch back and forth between these two. But other than tiling, if we really zoom in here, again, I'll switch back and forth. Here is Terrain Simple that I created in Shader Graph, and here is Terrain Lit that's using the code version of the shader. These two shaders look fairly similar, but this one is only doing 9 texture samples instead of 13. So that should be a good performance savings for us. Again, I'm not going to go into all of the details of how this works because the next series that we're going to cover on the channel is going to be specifically about terrain shaders. Okay, let's take a look at our list here and see what we're going to be doing next. And it looks like our next one is going to be the moss shader. So let's take a look at that. Our rocks, if we come over here, you can see our rocks have all of this moss growing on it. And I've created these fins that give us some 3D moss. And if I move out here, the moss is kind of expensive. So when the rock switches from LOD 0 to LOD 1, I make that moss go away. So we're not drawing it all the time. We only draw it kind of when we're close up to the rock here. But we want to optimize this moss shader. So let's take a look. We've got a texture here that is doing color and alpha. And we've got another texture here that's a normal map. So we're only doing 2 texture samples. So that's fairly optimized already. But I can optimize it a little bit more if I just remove this normal map. So we're sampling our normal map. We're doing a square root operation here to reconstruct the Z component of the normal. And then we're doing some normal strength calculation. So there's an extra texture sample here and a little bit of math going on to do this normal calculation. And if we look at our moss, and especially from the distance that we normally see the moss, that may not be worth it. Let's take a look and see what happens if we switch our moss material from using this shader to the optimized one, where I've actually removed that normal map. Here you can see that I'm only sampling 1 texture here, and the normal map and the extra math that we were doing is gone. So we'll select our moss material here and come down to moss fins and switch it to moss fins optimized. Now you can see because our normal map is gone, it did flatten out some of the detail that we were getting on our moss, which may not be what we want, but it is going to run faster. So we'll want to measure that and see if the little bit of quality loss that we're getting is worth the performance gain. I don't know. I think the moss doesn't really need all that much detail. It looks complex enough just because of the because of all the triangles that we're using, and so we may be able to get away without sampling a normal map on that one. All right, if we take a look at our list here, looks like nettle is the next shader that we need to optimize. And in our scene, our nettle looks like this. It's just these little plants here with kind of their broadleaf underbrush. All right, so let's find our terrain nettle shader. You can see that in this shader, let's see. I'm looking for texture samples because that's going to be our number one area of optimization. I only have one texture sample here. We're just doing red and green. Actually, let's find this texture and take a look at it. So here you can see I have my normals packed into the red and the green channel. And then in the blue channel, I kind of have this thing that's maybe like ambient occlusion. I think that's what it is. And I'm using ambient occlusion to shade my color and do a whole bunch of other things. So I'm only doing one texture sample here, which is kind of surprising. But for our normal map, you can see we're using this normal reconstruct Z. And that's using a square root operation. So instead of reconstructing the normal, what I'm going to do instead is take this normal data and instead of calculating the Z component, which is what I'm doing in that node, I'm going to use just a solid value. I'm not even going to calculate it. I'm just going to use a hard-coded value. And normally I would take the X and the Y and just append a 1 value here for the Z. But in this case, I'm using a value of 0.5. And the interesting trick about this is the lower this value is, the stronger the normals are. And let me show you what I'm doing over here. So here is our normal that I'm reconstructing over there. And then over here, I've got this normal strength node that I'm using to make the normal stronger. And if we take a look at our material, you can see that I have my normal scale parameter set to 0.2 right there. And so what I can do instead of using this normal strength is just lower this value from 1 to 0.5, and that will strengthen my normal just inherently. So what I'm going to do is skip this normal reconstruct, and instead I'm going to split my X and Y channels of my normal and then append it with 0.5 and pass that in. And then I'm going to skip my normal strength node here and just wire this over directly into my normal out. So I've saved just a little bit of math. I'm no longer calculating the normal strength, and I'm no longer calculating my normal reconstruct Z. And I'll save this here, and when we switch back to our scene, you know, our nettle plant looks almost exactly the same as it did before, but now it's running with simplified math in the shader. It's only doing one texture sample, and it was all along, but I was able to reduce the amount of math that I'm using to deal with the normal, and that should make the shader run faster. All right, let's see how we're doing on our list. Looks like we've got some more ferns. We have our rock shader next. So our rock shader is kind of an interesting one. Let's take a look at this. You can see that I've got a bunch of these different modules here. Over here on the left, you can see that my base textures are already just packed into two. I've got color and smoothness here, and I've got normal and occlusion here. So I'm doing a pretty good job of packing texture samples. Then I've got a module here that's applying micro detail or macro detail to my rocks, color bleaching, micro detail, and then moss deposition. And then finally, my last little unit here is for rain. And that applies like raindrops and drips and all that sort of thing. Now, I happen to know in this case that I'm not using color bleaching and I'm not using rain. There's no rain in my scene. So I can simplify this shader by removing the color bleaching unit and the rain unit and just kind of consolidating things a little bit. So that's what I've done. I've taken my rock shader and I simplified it by removing the color bleaching and rain items. So now my rock shader should be doing less math. So what I can do is I can take all of the materials from my rock shader, and instead of applying rock to them, I'm going to apply the rock optimized shader to them instead. And that should give me a nice little performance boost. All right, I think the last shader that I wanted to look at was the one for the grass. So let's go ahead and take a look at our grass shader here. The interesting thing about our grass, actually, let's just switch over to our scene. Yeah, so here's our grass. You can see it's got some really pretty looking translucency. And the interesting thing about the grass is it looks pretty good when we look at it from this distance, but then when we zoom in, you can see that there's no texture detail happening here at all. So this shader is actually pretty optimized already. We're not doing any texture sampling at all. We are doing some fairly complex math up here in the vertex shader to calculate the bend and the translucency. But the vertex shader math is fairly simple and not too complex, and it's happening in the vertex shader, so it's already optimized. Now, if we take a look at the pixel shader, there is one interesting thing that's happening here. Here's the normal, and I'm calculating the normal in the vertex shader and then bringing it in, and then I'm normalizing it, and I'm blending between that and this other normal that I'm doing a transform here, and then blending with the value of 0.4. And this is actually kind of complex math for calculating this normal. I wonder if I can get away with skipping this normalize, and then maybe just skipping this lerp and this transform altogether. So I'm going to try to get rid of all of these nodes and see if it'll make my grass cheaper. So here's the cheaper version. You can see that I'm just bringing in my normal, and then I've gotten rid of that matrix transform and the normalize. So this should make my grass shader a bit cheaper. Let's go ahead and apply the cheaper version of my grass to all my grass materials. All right, so I've got my grass materials selected here, and instead of grass, wind, terrain details, I'm going to pick grass, wind, terrain details optimized. All right, so I'll just save those materials, switch back to my scene, and they do a recompile, and I can take a look at the grass now, and I've still got my nice translucency of the grass shining, the sun shining through the back of the grass, and everything still looks pretty good to me. All right, there are a couple of more optimizations that I can make. So over here, I've got this decal that's applying mud to this rock, and if I move it around, you can see that, here's what the rock looks like normally, and here's what it looks like with mud applied. And so what I'm going to do to this decal is, I really don't think that the mud normal map is doing much to help here. And so I'm going to take this material projection mud, and let's take a look at this shader. In this case, I'm applying color, normal, and masks, and I'm doing that with a triplanar projection. And that can be kind of expensive. So what I want to do instead is just edit this shader so that it's not affecting the normals. So I'm going to switch over here to my graph settings, and where it says affect normal, I'm just going to uncheck that and also uncheck blend. And now when I switch back here, you can see my normal input here has been grayed out, and I'm no longer doing this normal triplanar projection. So that should make my mud decal quite a bit cheaper, because that's actually 3 texture samples that I'm skipping. And if I switch back here and take a look at my mud decal, you can see that I haven't really lost a whole lot of image quality. It still looks the same that it was. So I'm applying the mud color and the mud masks, but not the normal map. And that should make my mud cheaper to render. Okay, and then the last thing that I want to do is optimize my particle effects. So you can see here, I've got my waterfall particles. There's splash particles and mist coming off of the waterfall. Kind of lots of particle effects going on there. And if I find my particle materials, you can see, and I'll scroll down this list here, there are all kinds of different settings for my particles. Now, the ones that contribute the most to performance are lighting and also soft edges. So I'm just going to turn off lighting and soft edges on all of my particle effects. And that should give me a little bit of a performance boost. Now you'll see when I turned off lighting, my waterfall splashes here are quite a bit more prominent. So I might want to tone those down a little bit. I can just come in here to my waterfall one and adjust the opacity maybe so that it's not quite as prominent. There's my waterfall and my waterfall splash. I'll just reduce the opacity a little bit. Okay, so I've optimized all the shaders that I could find in my scene that were contributing significantly to my the expense of individual draw calls. What we should do now is do a build and see if it's affected our performance. Okay, so here we are in our scene, and you can see that our performance is a little bit better. Previously, we had about 296 FPS, and now we have around 308 FPS, so we've increased it. Now, one thing I do want to point out is we just spent a whole lot of time optimizing individual shaders, you know, removing texture samples and getting rid of normalization math and that sort of thing. And our improvement was fairly small. So we put in a lot of effort, but we got just a little bit of performance benefit. And this is the kind of thing that you have to watch out for when you're optimizing. Some things give you a really big bang for your buck, and some things take a lot of effort but just give you a little bit. But I would say that both of those things are worth it because they are improving our performance. So we spent a little bit of time, we went through individual draw calls, we optimized individual shaders, and we got a little bit of performance benefit, but you know, I still think that's worth it, and it's good to make sure that everything is running as fast as you can make it run. All right, so we took a look at shader optimization in Unity. Let's also jump over into our Unreal scene and take a look at the shaders there. Okay, here we are in Unreal, and there's a couple of things that I just want to mention up front before we dive in and start optimizing the shaders. The first thing is that this scene has been really nicely constructed with basically two main shaders that we're going to be dealing with. And so we only need to focus our optimization efforts on two shaders because all of the materials are based on these two main shaders. The other thing is, when I'm optimizing in Unreal, Unreal has this nice instruction count down here and a whole bunch of other stats that I can look at. And so it's really easy to tell as I take things out and put things back in if I'm increasing or decreasing potential performance. Now, one thing that I need to call out here about instruction count is that it's a very inaccurate way of judging performance. So you definitely want to make sure that you test the scene, you know, run it and measure the performance itself. You can't just depend on the instruction count to tell you if the shaders are going to be faster. But if you see that instruction count number go down significantly, it is a pretty good indicator that you're going to be improving performance. So it's nice to have that in Unreal to be able to see when you're making changes, if those changes are probably going to improve the performance or not. Okay, the main theme that I've noticed as I've been looking at these shaders, we have this one here called MS Custom General, and this other one called M Smart Master 02. And the main thing that I've noticed when I've been looking at these is that they've added a lot of tools in here for allowing the roughness and the normals and the base color to be adjusted in the materials to speed up the process of production. And so what you can do is, add a tint to the base color and change the way the base color works in real time as you're looking at the scene. And that improves the speed that you're able to put scenes like this together. But what you're doing is making your shader more expensive for every pixel, for every frame, and you're sacrificing, interactive performance in your scene for speed of development. And that can potentially be a good thing, but it also means that your end product is a little bit slower because you use some techniques that allowed you to develop the product faster. And so let me show you what I mean. So if we come here into MS Custom General and we come over here, all of these settings here that are happening in this little loop-de-loo thing are for adjusting these parameters. So here we have a material function that adjusts specular. And here we have a material function that changes the hue, saturation, and value of the base color. Down here we have some controls for adjusting the roughness. You can see the roughness offset control there. And here we have controls for adjusting normal. So all of these things are in the base textures, but then in the materials in the game, you're able to adjust them. And really, it would be much more efficient if these things were adjusted in the base textures themselves, instead of doing the math in the shader every pixel, every frame, because you're basically paying a performance cost for making these adjustments. So let's go ahead and optimize this shader, and we'll see if we can leave some of these things out, and if it makes a performance improvement, and if it reduces our quality. So right now we're looking at about 539 instructions. And what I'm going to do is just skip all of these adjustments that are being made and just leave them out. So we can skip this metalness adjustment. We can skip this metal at glancing angles adjustment. And then there are a couple of other things that we can skip here as well. So this material function is applying wetness to the shore. And I've seen this kind of effect made before. Basically, they're saying, like, in the world, my water line is at this particular height. And so anything below the water line is going to have wetness applied to it. And that's nice, but the problem is, like, I'm nowhere near the water in this scene that I'm looking at right here. I would have to exit the cave and go down to the ocean level there to actually see this effect. So we're paying for this effect every pixel, but we're only actually seeing it at the shoreline where the water meets the land. And so I prefer to do this kind of an effect using a decal, where I can put that decal where it's needed and pay for it right there, but not pay for it everywhere else. So we're going to skip this shoreline wetness effect. And if we needed to put it back in, I would create a decal and put the decal in to do it and not do it in the shader where we're paying for it all over the place. We also have this RGB noise overlay. And this is nice, but again, this is the kind of thing that could also be done in the base textures instead. And then we also have this node here, which is optimizing ray tracing. And what this does is, for things like ray trace reflections, it simplifies the shader significantly so that when a ray hits the surface, that result of that material is a lot cheaper. So we're actually going to leave that in because it's a really nice improvement. And so what I can do is I can just skip over all of this and grab the results coming out of this MF-based surface adjustments and just wire that directly into my my ray tracing material function over there. So I'm just skipping all of this and just jumping right to here. And we'll save this and take a look, and you can see that our shader has gone from over 500 instructions down to 363. And we've saved it, so we're looking at the scene now. And I don't know about you, but I didn't see any change in the visual quality of the scene at all. It still looks the same to me. There may be some very subtle things, but on the whole, you know, we just cut out about a third of the instructions in our shader, and it made almost zero visual difference here. So that's a really nice optimization. Let's step back and see what else that we can do to improve this. If we come in here, this is called MF Base Surface Adjustments. And again, there are a whole bunch of controls here for changing the values that are in our textures. You know, we have desaturation and contrast and brightness and tint and normal intensity and roughness adjustments and metallic adjustments. Lots of ways of adjusting those material parameters when really what we should be doing is making those adjustments in the textures. It does take a long time to open all of those textures in your photo editing application and make these adjustments a little bit at a time and save and re-import those textures. I will definitely admit that that process is slower than just moving these sliders. But when you have all these sliders in your shader, you're doing those adjustments every pixel, every frame, and there's a significant cost. So let's go into this base surface adjustments material function here. See if we can leave out some of these adjustments. So here we're doing contrast, brightness, and albedo tint. And I'm fairly certain that if we leave out that, it's going to change our scene too much. Let's switch to our buffer visualization base color. So this is what our base color is looking like now. And if we leave out all of these color adjustments here, we can just go directly from, let's see, we can just go directly from our layer 0 color and skip all of this and just wire that directly into base color. If we save this, yeah, I'm pretty sure, see, they're really leaning heavily on the ability to adjust these things to balance the scene and to make it feel cohesive, and they're using these adjustments. So we're not going to be able to skip this because of how heavily they're relying on these adjustments. Now, again, I think these adjustments should be made in the textures instead of in the shader, but they're doing them that way. So we can't really skip that step without losing too much quality. We might be able to skip our normal adjustment step here. So let's see if we can wire our normals into here, and we'll just switch to our world normals, and we'll save the shader. And looks like that one's good. We can skip our world normals without too much quality loss. And it looks like we saved a couple of instructions doing that. Let's go ahead and see if we can do the same thing here for our roughness and for our metallic. So for our roughness, I think that we can just grab the result of this switch and skip all of the other adjustments here. Let's switch our buffer visualization over to roughness, and we'll see what kind of a change this makes. So we're going to grab our roughness from this switch and just wire it directly into our roughness here and save this. Oh yeah, some of these objects have, oh no, it works. You can see that there's a little bit different roughness range on some of these than others, and they've used these controls to kind of bring them into a balanced range, but I think that we can probably get away with skipping that. Okay, let's look at our metallic. I don't think many of our objects are actually using metallic, so let's just grab our input metallic and wire it into our metallic here, and we'll hit save. And yeah, those changes are probably acceptable, and you can see that again we've reduced our instruction count down maybe 15 instructions or so. We've gone down to 353. All right, so I think we started out at about 540 instructions. So now we're about 353. That's a really good optimization. We were able to skip a whole bunch of unnecessary adjustments and reduce the cost of our shader quite a bit just in terms of instruction count. Of course, we're going to measure at the end and see what kind of a performance improvement we got, but at least we know that we've reduced the instructions. All right, let's take a look at M Smart Master 2. So again, we have a couple of adjustments here at the end. This shader is not doing the same ray tracing optimization that the other one is doing. So let's actually go ahead and copy this MFRT optimize and put it in our Smart Master. We're going to skip over the basic shore wetness and the RGB noise overlay and just bypass that and add in this MFRT optimize. Now, take a look down here. This shader is using 878 instructions, which in my mind is just insane. But, you know, you can't argue with how beautiful it is, that's for sure. Okay, by skipping these two functions, we've reduced it by about 100 instructions, so that's good. We've already done a little bit of work in this shader before when we were working on our nanite optimizations, when we were getting rid of evaluate WPO and pixel programmable. So when we did that, we got rid of these contact shadows that we were calculating. And we also got rid of this PDO shadows here. Let's see, there's some crazy, like, this specular ducking that they're doing here. I think that we can get rid of that. Just disconnect this wire here and leave specular alone. And we've reduced our instructions a little bit there. Let's see where our roughness is coming from. We have our roughness coming in here and getting adjusted by a bunch of things. So let's actually wire our unique roughness just directly in over here and see what kind of a benefit we can get from that. Okay, that's taken us down another like dozen instructions or so. And then let's see, we've got our normal coming in here, roughness, pixel depth offset we've set to 0. Let's go a little bit further over here and see what else that we can do. Okay, we're doing a bunch of things here to adjust our base color and our base normal, and I think that we can skip that and just go directly from unique base color to combined base color over here. And the same thing with our normals. We can just go from unique normal to combined normal. We can leave out this masked surface overlay stuff that they're doing. And you can see, wow, that dropped us down quite a bit. And if we save this, take a look at our scene again. And again, almost zero change that we can notice. Now, another thing that I'm seeing here is we're doing some crazy work here to distort our UV coordinates. And this is to kind of get rid of the fact that some of our textures are low resolution. They get rid of the low res filter look by scrambling the UV coordinates around. But I really think that this is unnecessary. So we're passing these highly edited UV coordinates in, but I'm just gonna pass our UV coordinates in directly like this. And you can see that's dropped us down to just around 600 instructions. And again, very little visual change. Okay, I did find one more thing that we can optimize here. This detail AO is being calculated over here in this section where we're doing like a ton of texture samples and calculating lots of detail layers. But if we come over here to our debug views and come under buffer visualization and pick ambient occlusion, you know, this visualization is completely solid white. So I don't think that's doing a whole lot for us. But if you'll notice, our instruction count is 603. If I come over here and get rid of this connection from detail AO into ambient occlusion, now our instruction count dropped to 280. So almost reduced our instructions in half. And if I save this, again, you know, I'm not seeing any quality degradation in our scene here at all. So we've taken our shader that used to be maybe, I think it was 887 to begin with, down to 280 instructions. And to my eye, let me just move this out of the way and increase this here. You know, to my eye, our scene looks the same as it did before. We've optimized those two shaders and made our scene supposedly run a lot faster by doing that. But I don't think that we've lost a whole lot of quality. Let's go ahead and build the scene now and see what kind of performance improvement we got. All right, so here's our scene after we built it, and it looks like we're getting like almost exactly the same frame rate as we were before. So we put a bunch of effort into optimizing those shaders, and it didn't seem to have made much of a difference. And there is something good to be learned from this, and that is we need to do more profiling. I think probably what happened is that we're bound by something else other than the shaders. And so we need to go back in and figure that out using picks and whatever other profilers we have. Taking a look at our stats, it looks like our frame time is bound by the draws that we're doing. So maybe if we figured out how to reduce the number of draw calls, that would improve our performance more. Okay, well, that about does it for today's video. We took a look at diving into individual draw calls and improving shader performance using the shader optimization steps that we took a look at the beginning of the video. Thanks a lot for watching, everybody, and come back next week. We're going to dive in and do just a little bit more optimization before we move on to our next series of videos, which is going to be, again, on terrain and landscape shaders. All right, have a great week.